Hello everyone, this is lecture 6. It's about system of different equations. In this lecture, we're going to use system of different equations to model certain situations in the ecosystem. And one of the first model that we're going to look at is the classic prey and predator models. In the next lecture, also about system of different equations, we look into modify the classic prey and predator models to see the variety of assumptions that we need to make in order to make the model better and more realistic. So learning objectives of this lecture is of course about modeling system of different equations and understand prey and predator models. Before we jump into model prey and predator model using system of different equations, I'm going to recap what we have learned so far about different equations. So we want to look into model difference of changes as a constant rate. So for changes, we have delta a sub n equal to a sub n plus 1 minus a sub n. This is the difference equations, and this change is at the constant rate. For k is a positive constant. Given the initial value a sub 0, you can calculate the value of a in the next time period, which is a1. When you know a1, you can calculate the value of a2, so on and so forth. So in general, you can solve for a sub n plus 1 in terms of a sub n as follows. So you move a sub n to the right hand side, and you get a sub n plus 1 equal to a sub n plus k times a sub n. As you can see, a sub n is a common factor on the right hand side. You can factor out a sub n, and you get a sub n plus 1 equal to 1 plus k times a sub n. Instead of writing 1 plus k, which is a constant in general, I'm going to substitute 1 plus k with a constant r. And my model becomes a sub n plus 1 equal to r times a sub n. And the general solutions have been derived in class already, and the general solutions is of the form of a sub n equal to r raised to the power n times a sub 0, for a sub 0 is the initial value. So the general solutions relate the constant rate of change to the exponential functions. And depends on the value of r, you either have an exponential growth or exponential decay. So in the case of r greater than 1, you have exponential growth. And when r is between 0 and 1, you have exponential decay. In addition to model the difference equation using a linear growth factor, in this case you have k times a sub n. You can also use another growth factor, it's called logistic growth factor. So if you have the change to be delta a sub n equal to a sub n plus 1 minus a sub n, this is equal to k times a sub n. In addition to that, we're going to include the term 1 minus a sub n over capital L, for capital L is the carrying capacity in this case. This model is more realistic because the growth of populations will reach a certain carrying capacity, and then the population will stay stable as time goes on, or as t go to infinity. Whereas when you have a linear growth factor, the populations can grow as an exponential rate and increase to positive infinity, which is not realistic. Even though it's not realistic, it's still a good model to look at when you look into population growth or population decay of a species. So this is called the logistic growth model or growth factor. Again, this is a nonlinear growth factor. So this is just a quick summary of different equations that we can use to model the different changes in populations. Now before we jump into a prey and predator model, I'm going to give you the definitions of equilibrium values. So a value at which there are no more changes in the system is called an equilibrium value, or a fixed point, or a steady state. Alright, so we have enough information to model a prey and predator using a system of different equations. So again, this is a classic prey and predator model. In the next lecture, I'm going to modify this classic prey and predator model to come up with the variety of prey and predator interactions. Alright, so instead of just using prey and predator, I'm going to substitute that with two different species here. I'm going to use rabbit for prey and foxes for predator. So we're going to consider two species in the forest, rabbit and foxes, where foxes eat rabbit and there is enough food for rabbit to survive in the forest. We are interested in modeling the interaction between prey and predator, in this case rabbit and foxes, and investigate the long-term behavior of the two species. Because the forest is a complex ecosystem, we need to make assumptions to simplify the model. So we're going to employ the following assumptions. So the first assumption is there is enough food for rabbits and the population of rabbits increases by a constant rate in the absence of foxes. So from this first assumptions, we know that population of rabbits increase by a constant rate, and you can relate it back to exponential function as you see in the first page. So this is the exponential growth for the rabbit populations. Now rabbit population decreases as a result of the interaction between rabbit and foxes. This makes sense, right? Because foxes going to consume rabbits, and therefore the populations of rabbits will decrease. For the third assumption, the rabbit population is the only source of food for the foxes. Therefore, in the absence of the rabbits, the population of the foxes decreases by a constant rate and die down. In the third assumption, we're going to see the exponential decay in the populations of foxes in the absence of rabbits. For the fourth assumption, the fox population increases as the result of interaction between rabbit and foxes. Okay, and number 5, no interaction with all the species. So the ecosystem that we're considering is quite complicated enough by itself. So therefore, we just want to look into the interaction between one species of prey and one species of predator. This is a very basic model, and we just want to see the interactions where there are just one species of foxes and one species of rabbit. Also, there's no immigrations from to the forest, and no harvest and hunting is allowed in this ecosystem. Now we're going to get some terminology here so that we can use them in building of the model for rabbit and fox populations. So I'm going to call R sub n to be the populations of rabbit at time period n, and F sub n to be the populations of foxes at time period n. And to build up the model for rabbit populations and foxes populations, what we're going to do is we're going to follow the assumptions that we make at the beginning here. All right. So to build up the model for rabbit population, I'm going to start with assumption 1. So again, assumption 1 is that we assume there is enough food for rabbits, and the population of rabbits increases by a constant rate in the absence of foxes. So from assumption 1, we say that the change in the populations, so in R sub n plus 1 minus R sub n, is going to increase as a constant rate of k1 times R sub n, where k1 is the natural growth rate of rabbits in the absence of foxes. And as usual, we're going to assume that k1 is greater than 0. We want to have a positive growth factor. Now we're going to use this equations we just got, R sub n plus 1 minus R sub n equal to k1 times R sub n, and modify the equation so that we can incorporate the second assumptions in the model. So the second assumption say that the rabbit's population decreases as a result of the interaction between rabbits and the foxes. So from assumption 2, originally we have the equations of the form R sub n plus 1 minus R sub n equal to k1 times R sub n. Now you need to subtract the populations of rabbits due to the fact that there is interactions between rabbits and foxes. So this decreases can be written as alpha times R sub n times F sub n, where alpha in this case is the attacking rate of the foxes, or you can assume this value to be the death rate of rabbits. And we also assume that alpha to be a positive constant. In the terms R sub n times F sub n is technically showing the interaction between rabbits and foxes. So that's it for the assumptions of rabbit populations, and we're going to use these equations, I call this equation 1, in the system of different equations for the ecosystem that we want to analyze. Now we're going to move on to come up with a model for the fox populations, and we're going to use the assumption 3 and 4 for this fox populations. From the assumption 3, we have that the rabbit population is the only source of food for the foxes. Therefore, in the absence of the rabbits, the population of the foxes decreases by the constant rate and dies out. Right, so the population's change can be modeled using negative k2 times F sub n, because this is exponential decay, and also this is the linear factor but in the decreasing manner, where k2 is the death rate of foxes in the absence of rabbit. And we want to assume that, again, k2 is a positive number. Then we're going to use this equation and incorporate assumption 4. You have that F sub n plus 1 minus F sub n equal to negative k2 times F sub n. Now for assumption 4, the fox's population increases as a result of interaction between the rabbit and foxes, right? Because foxes consume rabbits, and therefore they can reproduce offspring, and therefore their populations will increase at the rate at which they hunt rabbits. So to incorporate assumption 4, we do plus beta of R sub n times F sub n, where beta in this case is the growth factor of foxes due to the presence of rabbits. So this is the second equations that we're going to use in our system of different equations. And we say that from equation 1 and equation 2, we have the system of different equations for the prey and predator models as follow. You have R sub n plus 1 minus R sub n equal to K1 times R sub n minus alpha times R sub n times F sub n. F sub n plus 1 minus F sub n equal to negative K2 times F sub n plus beta times R sub n times F sub n. So this is the system of different equations modeling prey and predator model, more specifically rabbit and foxes species. Next, we're going to see the interactions between these two species using the system of different equations. We want to investigate the long-term behavior of these two species. Eventually, we're going to visualize the solutions of the system of different equations and can draw some conclusions from the visualizations. So next, what I want to do is I want to find equilibrium values. And to find equilibrium values, by definitions, equilibrium value is the value at which there is no more changes in the system. So that is at certain points there's no changes in the populations of rabbits and there's no more changes in the populations of foxes. So to find equilibrium values, we're going to set R sub n plus 1 equal to R sub n. Again, we assume there's no more changes in the populations, and set that equal to the population R, and R is what we're looking for. Similarly, when there's no more changes in the fox's populations, we're going to set F sub n plus 1 equal to F sub n equal to a capital F value, which we're going to find from this analysis. So to find equilibrium values, we set R sub n plus 1 equal to R sub n equal to R, and F sub n plus 1 equal to F sub n equal to F. And we're going to substitute R and F into the system to get the following values. So first, I'm going to substitute R and F into the first equation here. So I got R minus R equal to K1 times R minus alpha times R times F. So on the left hand side, we have 0. On the right hand side, you can see R is a common factor. So you take out R and you're left with K1 minus alpha times F. And here you can solve for the equations and you get either R equal to 0 or F is equal to K1 over alpha. Similarly, we're going to substitute R and F into the second equation, and we got F minus F equal to negative K2 times F plus beta times R times F. On the left hand side, again, you get 0, and on the right hand side, F is a common factor, and you take F as a common factor, and you're left with negative K2 plus beta times R. From here, you get that either F is equal to 0 or R is equal to K2 over beta. So from this analysis, we obtain two equilibrium points. So we obtain two equilibrium points. So you have 0, 0, which is a trivial solutions. And this solution say that over time, both rabbit and fox's population will die down. And we have another point, we have another equilibrium point of R, comma F equal to K2 over beta, comma K1 over alpha. And this is non-trivial solutions. So the first point makes sense that the rabbit populations and fox populations will die out due to certain scenario. Right. And therefore, there's no other analysis need to be done here. On the other hand, you have non-trivial solutions where the rabbit populations is equal to the ratio of K2 over beta and fox populations is equal to K1 over alpha. So in the case of R equal to K2 over beta, so the prey populations at equilibrium is determined by how quickly the predators die with the rate of K2 compared to how much they reproduce by consuming prey at the rate of beta. So at equilibrium, the rabbit populations is determined by how quickly the foxes die at the rate of K2 compared to how much they reproduce from consuming rabbits at the rate of beta. And for the ratio of F equal to K1 over alpha, To say that at equilibrium, the predator or the fox populations depends on how fast the prey reproduce at the rate of K1 and how effectively predators or foxes can catch and consume rabbits at the rate of alpha. So at equilibrium, the fox population depends on how fast the rabbit populations reproduce, or the rabbit reproduce as a rate of K1, and how effectively foxes can catch and consume rabbits at the rate of alpha. Some biological intuitions can be explained in this particular scenario, that for the case of R equal to K2 over beta, the prey population must be high enough to support the predator populations. If the predators or foxes die quickly with the high K2, more prey are needed to balance out that loss. If predators or foxes reproduce quickly with high beta, fewer prey are needed to sustain the predator populations. On the other hand, in the case of F equal to K1 over alpha, the predator population or the fox population is balanced by how much food, in this case, the rabbit, is available. If rabbits reproduce quickly with high K1, more predators can survive. If predators or foxes are very efficient hunter with high alpha, fewer predators are needed to keep the prey populations under control. Okay, now let's visualize these results that we got. Remember, we have two equilibrium points here. One is the trivial solution 0, 0, where all the populations in the ecosystem will die down. And we have another equilibrium point, that is R, F equal to K2 over B, K1 over alpha. So to visualize the results and to visualize this model, the long-term interaction between these two species, I'm going to use Excel for plotting and for analyzing the model numerically. So I'm going to use Excel to visualize the interactions between foxes and rabbit populations. And I'm going to use the system of different equations that you see in the notes. That is the equations of the form R sub n plus 1 minus R sub n equal to K1 times R sub n minus alpha times R sub n times F sub n. And the second equation is F sub n plus 1 minus F sub n equal to negative K2 times F sub n plus beta times F sub n times R sub n. So I'm going to create a first column here for time, and the second column is the populations of rabbits, and the third column is the populations of foxes. For time period 0, that means initially the value of the populations of rabbits is going to be 500, so this number is given to us. Right, so for foxes you have 120. And for time period 1, you need to calculate the populations of rabbit and foxes after the interactions. So we're going to use the system of different equations, obviously. And R1, or R sub n plus 1 for n is equal to 0, is going to be, or R1 is equal to R0 plus A1 times R0 minus alpha times R0 times F0. So obviously we're going to need some parameter for our calculations. So K1 we're going to assume to be 0.04. Alpha we're going to assume to be 0.0004. K2 is 0.08. And beta is going to be 0.002. So for time period 1, the rabbit is going to be R0 plus K1 times R0 minus alpha times R0 times F0. So I get this equation from the system of different equations, or the first equation in the system. Hit enter and I get the result here. So after the interactions, the rabbit population reduced to 460. Now we're going to do the same for the foxes populations. So this is equal to F0 minus K2 times F0 plus beta times R0 times F0. And after the interactions, the fox populations go up to 122. Now for time period number 2, you can track out the formula, and as you can see, this gives you a quite strange number. You have negative 4,360. So the issue is that when you track the formula down, everything will track down with it. So that is F12 now become F13, and K2 now become K3. F12 become F13 again, K3 becomes K4, so on and so forth. The issue is that we don't want the parameter here to be changed at every calculations when you track the formula down. So you want to keep the value the same throughout all the calculations. To keep this parameter's value the same, what you need to do is you go to the first formula here and you put the $sign in front of k, $sign in front of 2. Do the same here for k3, $sign in front of k, $sign in front of 3. Doing this, it lets the system know, it lets Excel know that I want to keep this value constant throughout all the calculations. And hit enter, and you can track the formula down one more time. And at this point, the population makes a lot more sense now. It's go down to 491. You should change the formula for the Fox populations as well, so that the parameter will not change when you drag the formula down to the next cell. So K4, you want to keep that constant. You don't want to change that. So $sign in front of K, $sign in front of 4, $sign in front of K, $sign in front of 5, and you track the formula down. Okay. In populations dynamic, you usually want to see the interaction between species through a long period of long period of time. So usually the time period can go up to 500 or 1000 or 2000. So it's going to take a lot of time and effort to actually type in the counting number here and also drag the formula down to, let's say, 1000 time equal to 1000 or time equal to 2000. So what I'm going to do is I'm going to input a formula so that it, by just using that formula, it can generate a column of, let's say, in this particular example, I want to see time period up to 600. So n is equal to 600. All right, so to do that, I'm going to go here in this column, in this row. Instead of 1, I'm going to do equal, and I'm type the command sequence. You can see sequence here. And for the choice in the sequence formula, you want to include how many rows you want to have. So in this case, 600 rows. Number of column, I just want one column. That is the column of time. The starting value is 1, and the stepping is going to be 1 as well, because I want to take one step at a time. Okay, so I need 600 rows, one column. The starting value is 1. The stepping value is 1 as well. You close the parenthesis for the formula. You hit enter. You will see an error, but that's fine for now. So the error, because there's 2 here, so you want to get rid of the 2, because when you type in the formula, it should be able to drag out to 600 or generate 600 rows from this point on. So you delete number 2 here, you should see that it generates 600 rows for you. Okay, so now what about the rabbit and foxes populations? So I'm going to get rid of this formula. I don't want to drag the formula down to 600 time periods, because usually maybe you have millions of data points and you don't want to track it down to millions of rows. Okay, so what you do is that here you have the y cross. You're gonna move it to here, and the y cross change to black cross. Double click on that, it's automatically drag the formula down to the row 600 for you. Okay, and you can see all the population or the number fill up to the 600th row. This value will make sense a little bit later because we haven't done any fox population yet. Now for the fox population, you do the same. You don't want to drag the formula down to 600. Again, there are probably millions of data points. In reality, you don't want to do that. So what you want to do is here, choose this cell, y cross, change to black cross, double click on that, and the populations will automatically generate for you up to 600 time period. So next, I want to visualize this data or this model by plotting the populations that I just generated using the system of different equations. So I'm going to plot 2 different graphs. The first graph is the population of rabbit and foxes versus time, and the second plot is the interaction between rabbit and foxes populations. So to plot the first graph that include time versus rabbit and foxes populations. Now you don't want to choose the data by drag your cursors down to include 600 time period. Again, there's going to be very time consuming to do so, because in the case of millions of data points, what should you do? All right, so what you do is just choose the first row. Next, use the combinations of 3 keys on the keyboard, Shift, Control, and downward button, and it's automatically choose all the values in the 3 columns for you. Now on the right slider, to slide up here because you want to place the plot on the right hand side of the table. Now let's plot the data here. You go to Insert, you go to Scatter Plots, and you're going to choose Scatter with smooth lines and markers. And this is what you're going to see. Right. So I'm going to change this a little bit more. I'm going to change the title a little bit, or the layout of the plot a little bit. So you go to Choose Plot, go to Quick Layout, and choose the first layout. And here, the title of the plot is going to be Prey and Predator Model. The horizontal axis is time. The vertical axis is population. Now I want to change the legend as well. I want to show that the blue curves represent the rabbit populations and the orange curve represent the fox populations. So I'm going to click on the legends. Either you right click and go to select data, or you choose the legend here and go to this area, choose select data, and you're going to change the name of series 1 to rabbits and series 2 to foxes, and you hit enter, or OK for that matter, and you have this plot showing that the populations of rabbits and foxes versus time. Again, we just want to stop at the time period 600. Next, we're going to visualize the population of rabbit and foxes around equilibrium points. So what we do is choose the last two columns here because we just want to see the interaction between these two species and ignore the time period. Choose the first row. Use the combinations of 3 keys, Shift, Control, and downward button, and it will select all the value in the 2 columns for you. Again, you want to go up to the top here because you want to place the graph right below the first plot. So with the data that you chose, go to Insert, go to Scatter Plot, and choose this scatter plot with smooth lines and markers again. So this should be the plot. So I want to change the layout one more time. So you go to Quick Layout, you change that to Layout 1. The horizontal axis should be rabbits population, and the vertical axis should be foxes or fox population. You don't want legend in this case. And the title is going to be rabbits versus foxes. Okay. And this is the initial value of 500, 120, and you can see that the curve spiral outward counterclockwise. And remember, we do some calculations on equilibrium values. You found 2 equilibrium values. One is at 0, 0, and the other one should be around here. And how could we know that should be around here? So let's do a quick calculations. So you have R equilibrium is equal to K2 over beta. So K2 over beta, and this is equal to 400, and F equilibrium is equal to K2 over equal to K1 over alpha. So the equilibrium point should be, in this particular context, in this particular example, or in this particular initial values of 500 and 120, the equilibrium point should be 400, 100. So it's around here. So the equilibrium point should be around here. And the curve spiral around that equilibrium point outward indicate that the equilibrium point is an unstable value, meaning that regardless of the initial value, the value of R and F will go away from that equilibrium points. Okay. So that's it for the first model. We're going to move on to lecture 7, where we modify the classic prey and predator model and incorporate different assumptions to see that there is a different variety of there are varieties of prey and predator models. One may be more realistic than the other. Thank you for watching the video. Please let me know if you have any questions.